Cambridge, ultracold atoms in quasi-periodic potentials, and optical quasicrystals.
Yeah, thank you very much. Thank you very much to you and also to Lev and all of the organizers for organizing this nice workshop. We already had a couple of very nice discussions on localization, on spectral properties, and on critical phenomena, and I'll try to touch up all three on them in this context. If there's one thing that you should take away from this talk, if you forget about everything else, because it's rather late in the day, it's that quasi-periodic potentials are a bit like disorder potentials, but more fun. So by training, I'm an experimentalist, even though I'll have a few theory slides in the talk. So just go easy on me in the questions, because, this is what I can talk about a lot. Okay, so let's start in 1D for the moment, quasi-periodic potentials. The one main standard quasi-periodic potential that people look at is the 1D Aubry-André model. So this is a tight binding model where you take particles on the lattice that can hop from one side to the next. In this case, it's written for fermions, but we also have it for bosons. And then the on-site energies are modulated. They're modulated in a sinusoidal fashion. And the key point is that this beta is an irrational number, which means there's no period in here after which the system repeats. It's not just a superlattice with period 5, 10, or whatever. In some sense, it's the limit of the period of the superlattice being infinite. And this has a lot of profound consequences. One of the nice consequences is that, like a disordered potential, there's a localization transition in here. It turns out that for this model, it's self-dual around the point where delta over j is 2. And the consequence of that one is that for exactly delta over j bigger than 2, all single particle states will localize. Below that, they're all delocalized, extended states, but above that, they are all localized. And they're all localized at exactly the same point. And in fact, if you plot the localization length of this model as a function of this delta over j, and that comes back to what we discussed at lunch, they are delocalized. You have a metallic phase over here for small delta over j, but then it becomes very strongly, very quickly, very strongly localized. So even if you have a factor of 2 above the localization transition, your localization length is already on the order of 1 lattice side. So in some sense, these systems localize later than real random systems. But if they start to localize, they localize very quickly catch up and go to very small localization lengths. And that's one of the key ingredients why we think that these systems are especially interesting for many localized matter. The other thing is that if I just go back to the system, the distribution of these on-site energies is, of course, long-range ordered. We know precisely what it's going to be at every lattice site. There's no randomness in there, which means that all of the distributions that we've heard about in the lecture will be different. They can, in principle, be computed exactly because you know exactly how everything looks like. You don't have to do huge disorder averages if you want to do numerics, because you know precisely how the structure is going to be. So you can be very sure if you say, for instance, to MBL numerics, that you are not missing out on one critical configuration that delocalizes everything and changes everything. Because you know there is no further randomness except for the choice of the offset phase phi here. Okay. So this localization transition is funny because when you think about normally what you get when you approach a transition, you approach a scale invariant point where everything just becomes a power law because there's no scales left in the system. When you think about this irrational beta, you can decompose it into a string of integers just using a continued fraction expansion. So you can always say it's like 1 over an integer plus some rest, which again I can write 1 over an integer plus some rest and can go on like this. And this gives rise to like a discrete scaling transformation where I go from one length scale to a length scale that's n 2 times bigger, then the length scale that's n 3 times bigger, and so on.
Okay, you don't have special configuration because you don't talk about. Do you have special system sizes that would like fit or not fit?
If you want to do numerics on this, what you find out is that if you now say take periodic boundary conditions and you take periodic approximants of your irrational number, which basically means I take this continued fraction expansion and truncate it after the first, second, third step or so on, then I get the best possible approximation of the irrational system. So in that sense, there is some special system sizes, but if you like take it to infinity, there's no problem, no. So one pictorial way to think about this is to say if the black dots down here are my original lattice sites, spacing 1, then I have this black curve here, which is my quasi-periodic potential. You see it has a period which is almost the multiple of the lattice period, but not exactly. So I'm thinking about the ground state. The ground state will, of course, live at the minima of this potential, so here, and then here, and then here. If I take the approximation, that I take here of taking this N1, that gives me this one. The remaining part gives rise to like a new potential living on the longer length scale. That's why I was saying you get this discrete scaling transformations. And if you take this one, you would expect that the approach to localization is slightly different now because it's not just a power law, but it will just follow discrete scaling steps. And these scaling steps are given by the numbers Ni. So that means you will not have traditional power law scaling, but you'll have something slightly different, which is kind of fun to look at. So for instance, if you take as this beta, the silver mean, where all of those continued fraction expansion, it's two periodic, all as number twos, then you get something which basically approaches the localization intuition almost like a power law. However, if you pick a slightly different beta, say the first 10 terms are twos, but then you go 6 periodic, then at some point you deviate from this and you get to a new approximate power law. For 8, another one. So a very small change in beta will of course change the transition very close to the transition point because the approach to discrete scaling transformation will be different. You can also like play funny games. You can say, okay, what happens if I have something where every second step is 2, every second step is 6? Then you get like a small rescaling step, a bigger rescaling step, and so on. And you get something that kind of wiggles its way towards the transition. It's never just a straight line. And if you get a random number of these ends, you get something that's very much non-periodic and is very different. But this in some sense is rather academic, because to really see this, if you look at the 10th digits, is you need like system sizes of the order of 10,000. For many of the cases, I'm just saying is, if you think about quasi-periodic models, you have to think about which beta you pick. We love the silver mean for reasons that become clear later in the talk. Many other people take the golden mean, or sometimes you just take very different systems. There's a lot of universality in here because you can take different quasi-periodic models. For instance, just the operant tree model, you can generalize it. You can also take a continuum model of a bichromatic lattice with the lattice the same. It turns out that the universality class that you get, in a sense, if I can call it a class, just depends on the beta, but it's the same for various different models. Okay, so how would we now introduce such a system in a real experiment? Switching to the experimental slides. The easiest way to do, which we did like 10 years ago, is to say we take one strong lattice to generate our tight binding model, and then we just take a second lattice, which is rather weak, which just gives this on-site modulation. And if we now take two laser beams, which have frequencies or wavelengths that are not a commensurate ratio of each other, then we exactly get this model where this beta is now just given by the ratio of the laser wavelengths. Now, of course, these are two real numbers, whether this is an irrational number or a rational number, you can't really figure out. But as long as you figure out that you stay away from the simple fractions, like 1/3 or 1/5 or something, you might have created a super lattice with a period of 100 or 1,000 sites. But because your system size is smaller than this, it's indistinguishable from the quasi-periodic case. So you can do a lot of things with numerics. For instance, if you say I take the first 2 or 3 terms, take a continued fraction expansion that's finite, and then get like a periodic approximant to the quasi-periodic function, which lives on, for instance, 100 sites or 111 sites or something. And that's a nice system to simulate.
What is the hopping?
The hopping in the operator entry limit, if you write down the operator entry Hamiltonian, you say that the hopping is constant and does not depend on the modulation. In the experiment, it depends on where you are. In the experiments that we did at that point here, we were like, the primary lattice was 7, 8 recoil deep, and the secondary lattice was just a few percent of that. Then the modulation in the hopping was below 1%. But you can, of course, go to this more generalized model. If you take the primary lattice down, have a stronger modulation, and then you get slightly different effects. So you can do both. And we'll see that a bit later in the talk.
In experiments, you just impose two lasers, make them interact, create this beating, and that's it.
So the lasers don't interact. The lasers just create 2 standing waves, and the atom sees the sum of the 2 potentials. And because the 2 potentials have incommensurate periods, they effectively see this incommensurate model. And that's what we did. And this is also what we used like in the early days of many-body localization to really look at whether you can have non-ergodic many-body states in there. So what we did at the time was to say we just create by hand a charge density wave where we just place particles, in this case fermions, on the even lattice sites. And then we let the system evolve under this quasi-periodic Hamiltonian, free evolution, waited some time and saw what we get. And whatever the evolution is, if it's ergodic on those time scales, then it will destroy this initial charge density wave because there's nothing in the Hamiltonian which would make a charge density wave an eigenstate, and there's nothing in there which would distinguish even and odd sites globally speaking. So ergodic time evolution would destroy the initial charge density wave, while if it persists for long times, then you know that you must have non-ergodic behavior, and the only reason to get that would be localization. So the quantity you look here is the imbalance. So you ask after some time t, how many particles are still on even side minus particles on odd sides. And then we did this, we measured this, and as a function of the interaction strength, T over J, which can be positive or negative, repulsive and attractive interactions, and as a function of the delta over J, so the strength of this quasi-periodic modulation, we saw a nice transition from like blue, low imbalances, that's an ergodic phase, to a non-ergodic phase up here, which is the many-body localized regime. You can see that it depends on interactions, but it was persistent to all interaction strengths in this case. So it was direct observation of MBL and everybody was happy. And of course, a few years later, the discussion started, is this a transient phenomenon? Is this just slow dynamics? Or is this something that will really persist in an infinite system also for infinite time? So the question of stability of MBL, where I think the debate is still going on. And the limit in a lot of this debate on the numerical side is that, of course, you can't do exact diagonalization for more than, say, 40 sites. So you're limited to small systems. Here in the...
You are very optimistic. Even out of that.
Depends. Okay, if I take single spin fermions or hardcore bosons with me as neighbor interactions, not for the full Fermi Hubbard, but okay, yeah. I'll give you credit, right? Okay. So anyway, in the experiment, that's not our problem. In the experiment, these chains can be much longer. What is the question in the experiment? Why is this not settled once and for all, just experimentally? Well, the answer is very simple, is that if I just plot the atom number that survives as a function of the tunneling times that we lose, we just have a system lifetime of a couple thousand tunneling times. For various technical things like photon scattering, light-assisted collisions, and so on, the atoms eventually get kicked out of the state. So it's a nice closed quantum system for a couple thousand tunneling times, but we can never tell you what, with these systems, cannot tell you what happens after 1,000,000 tunneling times because there's no system left at that point.
So just a comment on the diagram. If you could go back to the diagram, yeah.
This one, yeah.
Yeah, right. So U0 is not ergodic. It's actually non-localized, but not ergodic, right? Because it's not interacting.
True, it's non-interacting, yes.
It's a line that you cannot distinguish by that measure. It's not ergodic, but it's delocalized.
Sure, well, okay. In the limit of strictly ideal gas, of course, momenta unconserved, and so on. If you just go epsilon away from that, then of course you know that you're under the ergodic regime. Like when we teach the ideal gas in statistical mechanics, we say we assume it's an ideal gas, but we still assume there's enough collisions for it to thermalize. So in the same spirit, you would say the line you're talking about is absolutely thin, but just away from that line, you would expect the system to be ergodic.
That is a true statement in the thermodynamics. But in a finite system, not.
Yeah, okay.
So
at some point, you have KAM theorem and all of those things.
The students get that.
Yeah, that's true. There's a special slice here in the middle at the non-interacting line. That's true. Okay, fine.
How big the system size in experiment?
It depends on what you do. Typically, here you get like an order of 100 atoms in a system that's maybe 150 lattice sites long. So that's not our limit. The limit for us really is just that the system decays after a couple thousand times. Okay, so let me now.
Why results were shown for only 10 tau or 20 tau?
Because that was the first experiment. This is a few years later where it became clear that I took out many slides. So you look at the stuff, and when you look at what happens in the experiment, you see that, okay, over like 10 tunneling times, things stabilize. And then if I want to go into the details, it turns out that if I go to what we call a 1D system, which is the same as what Dave did, is to say, okay, you have this whole bundle of 1D systems because you have transverse lattices. It turns out that on the order of, again, 1,000 tunneling times, there is still tunneling between the tubes. So on that time scale, the system is not 1D anymore. And then the system is also not localized on those scales anymore because we have the perfectly same copy of the same disorder potential in each tube. So the transverse directions, even though they're very weak, they're not disordered. We have another paper later in 2017 or 18 where we also like disorder the other directions, and then that effect goes away. So we've done a lot. We're pretty confident that up to the limits that we can reach, which is basically the system size limit, everything looks nice and is understood and is localized. But of course, we cannot make an experimental statement over the long-term limit because finite time. Okay. Let me take maybe an excursion because up to this point, we think that quasi-periodic is maybe similar to random disorder. Now I want to show you something where it's very, very different, because it's this underlying complicated distribution which has fractality to it, and therefore has a very interesting topology. To get an intuition of where this comes from, one way to get quasi-periodic systems in 1D is the so-called cut and project method, where you say I start in 2D with a regular periodic lattice, in this case the square lattice. I cut out a certain stripe and project that down into a one-dimensional system. If I now take, say, an irrational angle here for my cut, the system that comes out here is not periodic. It's quasi-periodic. In this case, it's the Fibonacci chain, for instance. And it turns out that when you do this projection, these one-dimensional systems here can inherit the topology from the two-dimensional parent Hamiltonian. So people could see quantum Hall edge states, first Chern numbers in this 1D systems, and they could see like second Chern numbers and 4D topology in 2D quasicrystals. This was done in photonic systems. So if I now go back to my Aubry-André model, people also tend to call it the Aubry-André-Harper chain, because this model is also the 1D limit of the 2D Harper Hamiltonian, of hopping in the presence of a magnetic field, where of course you have Chern numbers and complex topology. Another thing that you realize is that what this already tells you is that the spectrum of this one, you would expect it to be a fractal, because the Hofstadter butterfly in 2 dimensions is of course a fractal energy landscape. So if I plot the spectrum of the Aubry-André model, and now we've switched and we call delta now V, just because it's a different paper with different authors, and they had different conventions. And we plot now the energy as of in units of V as a function of V over J. Then we can say there's one limit where the disorder fully dominates, where you basically say, okay, I have no tunneling and I just have a continuous distribution, or not continuous, but I have a dense distribution of my on-site energies in space. And then tunneling makes things more complicated, it becomes fractal. I have many, many gaps opening. The spectrum actually turns out is a Cantor set, if you're into fractality. How can you understand the spectrum, and what can you learn about the spectrum? It turns out you can do this very easily with a configuration space picture. Configuration space means that I basically, instead of having my index I, which like labels the sites, I'm thinking about the phase theta I of the modulation on that lattice site. So it's this 2 pi beta I plus my phi offset. I just call it theta I. And then I can map every lattice site in real space onto a position on the unit circle. Easy as that. The next thing I realize is that now states that are nearest neighbors in real space, so I go from I to I plus 1, they're like a phase 2 beta pi away in configuration space. And the last thing I realize is that because this is just a cosine, the vertical position directly encodes the offset energy. And why is this interesting? Well, this actually is nice because when I now do perturbation theory in the hopping, starting on this one, I get a very nice interpretation for the positions of the gaps and everything I want to know about the spectrum. And for instance, if I say, okay, well, I want to ask, why is the biggest gap happening exactly at this energy here? Well, it turns out if I plot my circle next to it, and I'm asking, where do two sites live in energy if they have the same energy, if two neighboring sites are degenerate? Well, the answer is where exactly these 2 points on the circle are 2 pi beta away from each other. So it's exactly at this point. And then if I do perturbation theory in the hopping, that's where I have nearest neighbors that are resonant. So I get my avoided crossing, and the gap opens up. So I understand where the first order gaps are. The same argument applies for the gap down here. I can now go further and say, well, this is the second order gap opening. Where is that? Well, it must be exactly at the point where two of these steps bring me from one resonance state to the next resonance state. So I can calculate exactly where all of the gaps are in the spectrum. I also know how many gaps there are, because there's countably infinity, because for first order, second order, third order, and so on, I get 2 gaps each. And really important, I can also directly, by just looking at the solid angle on the unit sphere beneath this line, I know how many states are there below this gap. And if I know how many states there are below this gap, then using the gap labeling theorem, if you know enough mathematics, I don't, but people do, you can figure out what will be the Chern number of those bands. So you can easily figure out that this lowest band up to the first order gap, if I ignore the small gaps inside, they must have a Chern number of +1. This must have a Chern number of -2, and this one again +1, because in total it must sum to 0. So everything you want to know about this complicated spectrum, you can just get from this unit circle construction, which is nice.
About the states, can you get the states also? I guess.
In the strongest order limit, yes. Because in the strongest order limit, you would argue, okay, if I do, say, first order perturbation theory, for most of the sites, the eigenstate are just the Wannier states. Just if I have this resonant pair, I get the symmetric and antisymmetric combination. So you can calculate the states perturbatively deep in that phase. And then there's something called the Thermalization problem, which tells you that these structures carry over all the way through the spectrum.
Comment here.
I'm sorry.
Limit V to 0, because the y-axis then V goes to 0. So where does this then correspond to the V to 0 limit?
So in the V to 0 limit, the spectrum in this unit, of course, diverges, because then the spectrum is like the spectrum then is 4J, right, from minus 2J to 2J. But if I plotted units of V and that V go to 0, it diverges. It's just that, yeah, it's a stupid plot for that limit. But it's a very nice plot for the limit that we care about where V is big. Yeah. Okay. So now, this is nice mathematics. Can I see this in the experiment? And we haven't done it yet, but we have seen first indications that it will work. You can see this by using a Fowler's pump. Fowler's pump means that you have a Hamiltonian, and you kind of change a parameter of the Hamiltonian in a periodic fashion. So like on this Archimedean screw, you turn the handle, and if you turn the handle in the right direction, you pump the water up. So we're doing a periodic modulation of the Hamiltonian. You expect that you see stuff moving in one direction or the other. And what is our handle? Well, for us, it's the offset phase phi of the second letters relative to the first letters. So the pumping just means that we slide the second letters, the weak perturbation, compared to our primary letters. We just start with particles here and we slide this over. And now we can do this charge pump in the strongest order in the deep lattice limit, where states are basically localized. So we do it with localized states. And actually, it turns out what happens is rather simple. The eigenstates are Wannier states. So if I put a particle on one lattice site, and now I start to turn the handle, this lattice site will move over along the circle until it hits the resonance, because now I have this one lattice site. The energy of lattice sites are plotted here. The one lattice site energy is going down, and its neighboring energy is coming up. So at this point, I just have a crossing, because I have tunneling, it's an avoided crossing, and I do a Landau-Sehner transition, and I hop from one side to the next side. And then I continue again along my circle until I do this again, and then I jump again back. So I hop, I hop, I hop, I hop, and I'm pumped to the right. And you can plot this. You put a particle on side 0, you start turning the handle, and you see periodically the particle hops one side to the right in this Landau-Sehner crossings. If you think about this in energy, you say, well, I have my 3 bands. I ignore all of the smaller gaps here, and then I just start up in the top band, and I just oscillate in the top band, and I get pumped to the right. And I'm protected by this gap. If I now plot this in real space, and I say I start with a lot of particles in the middle, just here at time t equals 0, and I start turning the handle and pump, then the particles in the top band and in the lowest band will pump to the right, and the ones in the middle will pump to the left, also with faster velocity. So this really gives me a topological pump that then separates out these bands. And it's even more fun if you look at this. What you plot here now is you say, okay, well, I might be protected by this gap. What happens to the charged pump if I add this order, real random disorder on top of the quasi-periodic modulation? At this blue line here, the disorder is strong enough for the gap to close. And you see nothing happens. I'm still quantized until much, much, much bigger. So I kind of a situation like this one where my spectrum is just a zoo of spaghetti. I'm moving randomly around the spectrum almost, but still my average slope is precisely quantized. I'm still in this regime. I can do the same thing in one of the middle bands. This is like a churn number 4 band. And it's even more impressive because now the plot here is on the log scale. So you see my disorder can be a factor of 100 bigger than the size of my gap, and I'm still protected. And configuration space allows us to understand what's going on here, because we basically can say, well, what happens is the sequence of Landau-Sehner steps. I go from side 1 to side 1 plus 1, I plus 2, sorry, from I to I plus 1 to I plus 2. And if I now say I put this order on there, I move down the middle side, then you will see that, okay, well, the first transition happens later, but the second transition happens earlier, so the average slope stays the same. And this only breaks down when I move the side down so much that the order of the transition changes. Then I get backscattering. So you can plot this, you can say, okay, as a function of the pump rate and the disorder strength, where are you quantized? Well, this gives you a very nice criterion. This red dashed line is just the criterion that I mentioned here. So it's very nice. It shows us that these quasi-periodic systems, they're not just standing in for disorder. They also have a lot of topological structure under the hood because it's a long-range ordered system. And you can make use of this. And you can have very interesting phenomena coming from that.
How much less is quasi-periodic of the order? If I open just periodically open the gap. molecular sample.
You're asking if can I do the same thing with a periodic superlattice?
Just opening, like, you're working on the first order gaps, right? So you don't need quadrilaterality always here out. We're using
I have to think about it because I never thought about it. My first intuition would be that most likely not, because you need this sequence where you go from always to the next side, always to the next side. My guess is that if the thing is periodic, at some point, because you have to come back to the original situation, it will not work, because at some point there must be a jump where you come back. But that's my guess. It's an interesting question to look at. It's a very good question to look at, actually. Okay, so now let's move over to 2 dimensions, where everything is a bit more complicated, and therefore we understand things a little bit less than we do in 1D. So what we do in 2D is we go for an optical quasicrystal. The story now is to say, well, we also want quasi-periodic things. We want something that's not periodic, but still has no randomness in it. So the idea here is you just play with rotational symmetries. You know that you can have a periodic crystal with 1, 2, 3, 4, and 6-fold rotational symmetries, basically because you can tile the plane with squares, you can tile the plane with triangles, but for instance, you cannot tile the plane with octagons. 8-fold symmetry just doesn't work out. Therefore, it was first a big surprise when people saw electron microscopy or electron diffraction pictures with a 10-fold rotational symmetry. That was Dan Schechtman in the early 80s. And there was a huge debate. Is this a quasicrystal? Do they exist? Or are these just quasi-scientists which forgot about twinning and a lot of other defects and so on? And when physicists can't agree on something for long enough, what will they eventually do? They'll ask the mathematicians. And then you ask people like Penrose, and he says, well, of course, you can have long-range ordered structures that are not periodic, like the Penrose tiling. The key thing here is that they are not periodic. They are long-range ordered. You don't have one unit cell, you have like 2 tiles, 2 types of unit cells, and certain matching rules to put them together. So you get these kind of self-similar structures with fractal properties. That eventually resolved the story and then got his Nobel Prize in chemistry, not in physics, 30 years later. So quasicrystals are not periodic, but long-range ordered. So there's again no randomness, same as with the quasi-periodic systems. And the key thing for them is that they have this forbidden rotational symmetries. And now we can reverse engineer that statement and say, if I now start building a lattice, which by definition has an 8-fold rotational symmetry, because I just take a square lattice, xy, plus a second square lattice, 45-degree rotated diagonals, and switch them both on at the same time, then the structure is just the sum of 4 sine square terms, so no disorder, no randomness, but it has 8-fold rotational symmetry, hence it cannot be periodic. And in fact, if you plot the sum of the 4 sine squares, you get a potential like this, which if you stare at it is very beautiful. It's clearly ordered, but it's also, maybe subtly, but clearly non-periodic. If you want to do the crystallography and you want to ask where are the latticesites, you end up with the Amann-Binka tiling, which is like the 8-fold cousin of the Penrose tiling. So you have the squares and the rhombuses, and that's it. And at this point, a big warning to all of the theorists, because people might think, oh, I now just use this one as a vertices of a tight binding model, and then just do physics on there. Don't do this. Do the following. We went through the work of really deriving a quasi-crystal Hubbard model for this, where all of the latticesites are now plotted here. The color of the latticesites, blue means very deep lying sites, red means very high lying sites, and the lines connecting them is the strength of the tunneling element. If you look at this, the crystallography is the same. So for instance, you have this kind of Rosetta type structure coming again and again. You have the same structure in here. If you, for instance, take like this blocks of squares and these blocks of squares just to orient yourself, they also show up in our tight binding model, say here, and okay, I said the one on the side here is this one. So the structure is the same. But the point is that the on-site energies and the tunnelings are very, very different than they would be just in the Amann-Binka tiling. So for instance, here you would say this is almost like a central spin, a little bit like SYK model. I have the site connected to 8 other sites. If you look in the real model, you realize, oh, this site is very deep. The sites up here are rather high, and there's this big well in between. It's this big potential well here around the site, which means that there's no tunneling from the inside to the outside. The site in the middle is almost disconnected. Another thing you realize here is that the strongest tunnelings you kind of get along this octagon, which is kind of cutting across these rhombi here, where you would not have tunneling in the simple Amann-Binka tiling. So the story is in the end is just don't use this one, use the full quasi-periodic Hubbard model. It's published here, so there's a link where you can download the model in arbitrary sizes if you want to try it for your own numerics. And there's a lot of physics that's understood by just looking at this model. It was a lot of fun project. Okay, so if I take this model, I calculate the spectrum of this quasicrystal, I again get a fractal structure. So this is the lattice depth, this is the energy. So here's the energy is weak things, here's a stronger lattices, and I again have a localization transition. So the color code here is the IPR. So red means strongly localized, blue means extended. And I can see that my ground state localizes again at a finite point, 1.77, 1.78 recoil in this case. And I can see that if I go beyond that, I get to a regime where all of the low-lying states are strongly localized, while stuff very high up in the spectrum is maybe not yet localized. So now thinking about many-body localization and so on in this kind of context will of course be a richer problem, because I can think about many of the underlying single particle states in different ways. So back to the experiment. How do we know that we actually have this quasicrystal? How do we know that the story works out? Here we do something that it's a bit like the Pratt method that Dave was saying this morning. It's a Kapitza-Dirac pulse. So we flash on the lattice for a very short time on a BEC. So here's our BEC. This is time of flight, so momentum space. We flash on the lattice for a short time, and that's a bit like electron diffraction of a thin sheet of material. The atoms can diffract to h bar k in any of the 8 lattice directions, and they can end up at any of those 8 points here. So we see the octagon that you would expect from the 8-foot symmetric case. And now what makes this very different from a periodic lattice is if the pulse is longer, that you allow for multiple scattering, it does not form a regular graph. The reason being that now from this point onwards, I can again go to an octagon of 8 points, and again and again and again. And it turns out if I have the pulse longer, I get very beautiful, very complicated patterns like this. One particular one is this one. What you see here is you have these kind of set of peaks. You see they're all scaled. There's these series of octagons in here where the relative distances between them, the scale is going by the silver mean, 1 plus square root of 2. If you think a little bit, you realize where the square root of 2 comes from, because all of your 45 degrees, sine 45 degrees, 1 over square root of 2. That's why the thing is incommensurate, and that's why this number peaks shows up everywhere. We observe this self-similarity. If we would go for longer and longer pulses, the set of points in here would become denser and denser and denser. So ultimately, I initially said it's a fractal, but it's not a fractal because it's actually a dense set of points in there. So every point of every red, we'll come to the middle. To observe this to this level, you really have to work hard because you need to be very perfectly non-interacting with your atoms. Otherwise, you get so many scattering spheres that the whole thing just blurs out. So we can observe up to the 9th order by really fine-tuning the interactions to really make them vanish. And if you now try to do crystallography on this one, you say, okay, well, normally I have my 2 basis vectors, x and y, and I can index every point in my reciprocal lattice vector by just going n times x, y times, or m times y, and I can reach every point. Here you realize that doesn't work. For instance, to reach this point up here, what you now need to do is you need to also introduce this diagonal term. Otherwise, you can never get to this point. And if you want to get to this point, even that's not enough. You also have to introduce the diagonal term, or diagonal and anti-diagonal term. So if you want to index any point on this plate, you can index them with 4 integers, and it's really a 4 tuple that you have. So you can think about this one as like a synthetic lattice, a periodic lattice z to the 4 in 4 dimensions. So when you think back of cut and project, it's a simple cubic, hypercubic lattice in 4 dimensions that we've projected down into 2 dimensions and therefore becomes quasi-periodic.
So I'm gonna picture there are these outside the second ring, there are these octagons of 8 points where there's one right, one in the middle, and
For these ones, for instance, yeah.
is that easy to understand where that comes from? That's like
Yes, these are just, so there's 2 things about this. First of all, this is just higher orders. This is just higher orders, and they are weaker because there is many paths going to them, and some interfere destructively. If you have very sharp eyes, you might realize that they are a bit not perfectly an octagon, they're a bit skewed. And the fact that they're a little bit skewed, this is the way how we now align our lattice. That means that not all angles are perfectly 45 degrees. And the thing is, if you look at the big structure, you would say, okay, this is pretty perfect. You're very close to 45 degrees. But if you look at, for instance, at the 9th order, if you have a 1 degree mismatch, it shows up at a 9 degree mismatch in the 9th order. So by looking at more and more of those structures, we now have even bigger pictures, better pictures where you really can fine tune all of this angle. The fact is, if you move a little bit away from the structure, topologically nothing changes because the number of points and everything stays the same. So we're not too worried about the small discrepancy here. Okay, so we have this kind of self-similar structure. And an interesting thing about this one is that if you want to get from, say, a point to another point that's very close, you can't just have a transition from here to here. You'd have to go via a long route to the right, up, up, diagonal, diagonal, down to come here. It's a little bit like the knight's move on the chessboard. The knight can move according to certain rules, which means it can't directly go to its neighboring side. It can only go there via a long complicated route. And the same thing that you have here. So if you want to be fancy, you say you play chess with a knight move on a fractal chessboard or a four-dimensional chessboard. Okay, so now back to thermalization, back to localization. I said that the ground state of the system will localize. And the question is, how can we detect this localization? So the standard way of detecting localization is I confine my particles to a small area, then I take away my confinement and I look whether the particles fly out or whether they get stuck where they are. The one thing that we, especially in the context of MBL, don't like about this is that we can never in a finite time distinguish from the particles that are being really trapped or being really localized or just moving very, very slowly. If you only have 1,000 sites, you can never say whether over 10,000 sites they would have moved or not. Here, because we're looking at the ground state, we have a different way of looking at this coming from the extended side, which is very, very powerful, I think. So the story goes as follows.
Yeah. So
Yeah.
So when you showed before, it's really not the ground state. You just hit the guy and just put it.
When I showed before, it's just crystallography. Yes.
So,
Yes.
good. And then how do you get the ground state?
How do we get the ground state? Okay. So what we now have to do with what we do if we want to get the ground state, we just very slowly ramp up the lattice and kind of adiabatically move into the lattice. But that's not what we're doing here yet. We'll come to that. So what we're doing here is just conceptually at the moment. We're saying if I have the BEC in free space, what's its wave function? If I forget about the trap, homogeneous system, the wave function is just a constant, right? Just a constant wave function, momentum is 0, so e to the I kx with k being 0 is just a constant. If I now switch on a weak quasi-periodic modulation, then the wave function becomes modulated. It will look like this. So gray is the potential and blue is then the wave function of the ground state. And this is now in the extended phase before the localization transition, so I get this extended quasi-periodic modulation. And now you can ask your dynamical question. You can ask, how long will it take the wave function to go from here to here? And the answer is not very long. This is rather quick in some sense because the particles only have to move a little bit to find like a good spot where they can sit. You just need local rearrangements of the density, so this can be very fast. Now, in contrast, if you go through the localization transition, where your ground state suddenly looks like this, and remember what I said before about quasi-periodic systems, once they localize hard. So this is just 10% or so above the localization transition. The ground state really looks like this. This is a numerical result. Now you can ask yourself, okay, how long will it take to go from here to here? And the answer is, well, of course, that time scale needs long-term, long-distance mass transport, which means if I start in the thermodynamic limit, I can go from here to here relatively quickly, but from here to here, the time scale will diverge. Which means now I can turn this into a measurement protocol by doing the following. I say I start off with my BEC, V0 is the lattice depth, this is time. I ramp up to a certain lattice depth in a certain amount of time, and I ramp back down again. And then I ask if I've done this all adiabatically, so if the system could adiabatically go from here to here and back, then I should very quickly end up again with all of the particles in the BEC. While if I do this across the localization transition, even though I ramp up much, much slower, I would expect that the particles go everywhere. They can't be adiabatic because they cannot adiabatically move from here to there very quickly, and they should get lots of excitations. Now, for time reasons, I don't show you the experimental result. It's a bit messy, it's in this paper. But if I just look at the numerics and I ask what is the time to get 99% of the atoms back into the BEC, you see that that time scale really diverges when you approach the localization transition. So this kind of question, where I can adiabatically transform the state and back, in some sense that's related to the fidelity susceptibility that we've been discussing in other talks. That's a very, very, very nice probe to like look at experimentally whether you cross a phase transition or not, especially a localization transition.
Is it clear why there's just one place that are localized as opposed to localized for a different spots?
Because this is the ground state. And it's kind of, if you take the thermodynamic limit of the quasicrystal, It's typically that you only have one deepest minimum. You can have up to 8 at very different parts of the system, but it's up to 8. It's a very finite, very small number.
It would, you know, if you went slow enough, you could actually get it for something here. And it seems like the energy of that state and energy of the state, which is someplace else, is so small.
Yes, yes.
that,
Which is exactly the point, that you will never be able to really go from a superfluid into the localized state in the ground state adiabatically. Because there's so many low-lying minima that you will always go into the combination of them. And then when you come back, you end up with a lot of entropy and very heated. That's exactly the point. You can't do it adiabatically. Yeah.
Randomly go to one.
You'll go into some kind of coherent superposition. But then you can't undo this when you go out again, because they all have slightly different energy. So while we're in the localized phase, they've picked up slightly different phase vectors. And then, yeah. If you look at the paper, there's the pictures that look beautiful when you come back. They have all of those extra higher momentum peaks, and you can analyze them in a lot of detail if you want to. We so far didn't do that.
And can I ask questions then? But that's only true if your interaction is exact.
Yes. Exactly.
In your experiment, I am wondering what is the control you have?
It's good enough. With the Feshbach resonance, we can really tune this very precisely. Yeah. I can give you a quantitative argument, but it's good enough for what we see. Let's come to that in a few slides. So because now we can ask ourselves, okay, what happens if we add interactions to the picture? So we're now just talking about the ground state of this many-body system, right? In the Anderson limit, u equals 0, all bosons will localize in the deepest well. And generally speaking, I will have one deepest well. I might have up to 4 or 8, but they would be at very different locations in the quasicrystal. I can't have more. That's guaranteed by the structure of the quasicrystal, because we know the potential very well. It cannot be that we have more than 8. So we assume we have 1. This is the deepest minimum, and the ground state for non-interacting bosons is, of course, all particles are in there. Now you can ask yourself, and this is in a deep localized phase where you can almost take like tunneling. Now you can ask yourself, what happens if you turn on very, very weak interactions, epsilon interactions? If you have many particles on here, then even very weak interaction give rise to a lot of interaction energy on that side because it's so highly occupied. So the ground state, you expect spillover. You expect that some particles will now not be in the deepest minimum, but in the second to deepest or third to deepest. And the point is, like what Antonella was discussing earlier, the point is that these second to lowest minimum will be arbitrarily far away from the lowest minimum. It's not arbitrary, we can calculate where it is, but it will be very, very far away. How far depends on the system size. The bigger you make your system, the lower the second minimum will be. And this means that, okay, you have this kind of spillover, you have to go into other lattice sites for very weak repulsive interactions. Now, if you crank up your chemical potential even further by, for instance, increasing the particle number or increasing the strength of the interactions, then you will start to like distribute the particles over more lattice sites. You're happy to pay a higher potential energy because that means you can lower your interaction energy a lot. And then you will start to hit local resonances. So then you will start, for instance, to hit a situation like this, where 2 neighboring sites are very close in energy, and then you put like a few more particles in the deeper side and a few less on the other one, and then you kind of create a resonance, and then particles can delocalize over these 2 sites, and they will form a little superfluid puddle. And if you then go even further at some point, you reach the chemical potential even further, at some point these local puddles will connect, and that's in the phase transition from the Bose class to the superfluid. So that's the picture what you expect in the many-body physics in here. So far, it's all just strictly ground state. And now we can start thinking about this. And this basically was, Matthew Fisher in the 80s was like one of the first ones to really discuss this in a lot of detail. So if you think about this Bose class phase, it's a very interesting phase. It's compressible. It's gapless because there will always be one puddle where you can still put another particle in at no cost if you have arbitrarily many puddles. It has no long-range order, so it's different from the superfluid. It's an insulator because there's no hopping, no connection between these puddles. So if you apply a very small chemical potential, you will not get a particle flow. They're localized. It's a localized phase. And I would claim now, this was not discussed at the time, that this phase will also be non-ergodic. Because when you think about it, the time scales that you need to have a rearrangement from this particle, say, going to over there, if you change the potential a little bit, the time scales will diverge, which means in the thermodynamic limit, you will never do this. So these non-local rearrangements, I think, are a very central argument. And the fact that ergodicity wasn't discussed at that point was because nobody was thinking about non-ergodic systems, many-body localization, and all of that. So how can we now look at this one in the experiment? Well, the answer is rather simple, because if we load the atoms very, very slowly into the lattice, as long as they are still in the superfluid phase, we can do this easily, and we get nice sharp peaks because we have a superfluid. If, on the other hand, we would go into a strongly localized phase, particles would localize to a few lattice sites, and in time of flight, you would see a big flat momentum distribution like in a mud insulator because you have no coherences in the system. So in fact, if you look at this, if you take a strongly localized system, in the non-interacting case, you get a big featureless blob. And if you now start to add weak interactions, you start to see sharp peaks on top of this, which gets stronger and stronger and stronger if you add more and more interactions. And these sharp peaks, well, sharp peaks directly mean long-range order, they're a signature of the superfluid. So we can directly see this phase transition from strongly localized to the superfluid by, in this case, changing the chemical potential by changing the scattering length. And then an experimental detail, but I think it can be important. Normally in a trap, you always have the problem that your trace transition is averaged over the different points in the trap, and then you never really know what happens, and you get like a weird mixture of things. In the Bose class to superfluid transition, it's rather simple to think about what happens. If you're below the localization transition, this is the trap, this is the density distribution, everything is superfluid. You have sharp peaks, strong sharp peaks everywhere. If you now go above the non-interacting localization transition, then the parts at very low density out here, they will localize first. They will turn into the Bose class, while the part at higher density in the middle, because it can smoothen out these little energy differences, will still be a superfluid. So we know that the Bose class will creep in the superfluid from the outside, and the high density center will localize last. That's, for instance, very different from the mod transition, where it's much more complicated. Which means that if we now look at the situation where we are in this situation, what we expect is a picture like this, and we see it. The condensate peaks stay sharp because we still have longish range order here in the middle, but they get smaller in amplitude because there's less particles in the superfluid, and the broad background gets higher because more of the particles are localized. And then if you go to like into the situation where you have fully Bose class, these sharp peaks have disappeared. And if you now just take, for instance, say the full width half maximum of your central peak, there's a very nice observable. It stays low as long as you have a sharp peak and then blows up to the size of the big peak when the sharp peaks disappear. So you really can make a plot like this, where as a function of lattice depth, you're superfluid, 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 and then bang, you're in the Bose class regime in the center of the trap. And these two red dots here is this picture and this picture. So the transition is incredibly sharp and very easy to see. Because of this, we understand what the inhomogeneous system does to us. So with this, we can now present the phase diagram, where we say, okay, what happens as a function of the lattice depth and as a function of the scattering length. So what we have down here, the light gray area, we have nice superfluid peaks. That's the superfluid. And up here, the blue area, we have no superfluid, we have no sharp peaks. That's the localized phase. And that's what we say is the Bose class. So now you can go on and say, okay, well, devil's advocate, are you sure? Just that you have no sharp peaks doesn't necessarily imply a Bose class. What are the alternatives? What else could it be? Well, lattice people will ask, could this be a mod insulator? You go into a deep lattice, maybe you get a mod insulator. Because we have this tight binding model, we know where the mod transition happens. And on this plot, it basically happens 2 rooms over there. So it happens at a couple hundred A0 and say 4 weaker lattice depths. So it's very far away from here. Then the question is this maybe just Anderson insulation? The Anderson insulator, well, the Anderson insulator is really only defined at this point here, at the non-interacting point. And we know that it's not just that the interactions are important because we see this big interaction shift. So we know that the system here is very different than the non-interacting system because otherwise the transition wouldn't have shifted. And this basically also, and this is therefore a direct observation of the 2D Bose class. And Marcos, this also answers your question, how do we know our interaction strength well enough? Well, you see that the data point for 0 A0 and for 2 A0, you see how different they are. And we know where the theory is, and we know what happens at attractive interactions. So we can pinpoint things that we really know we are on the order of less than 1 A0. And that's good enough for what we do in time of flight. Okay, so we have this Bose class now. We have this localized phase at very low energies. And then we can ask, okay, what does this imply for many-body localization? But I think before we go there, let's just have a little bit of fun with the system. Light relief if you want. Let me ask you the following question. I start off in the superfluid. So I have a momentum distribution like this. Sharp peaks is the superfluid. And now I'm at weak interaction, say 10 A naught. Now at time t equals 0, I jump in lattice depth deep into the localized phase. So what happens? We all know what happens on the long-term limit. The system will localize and will turn into a big featureless blob. But how would it localize in momentum space? What do we think happens? I mean, there's a couple of possibilities. We could say, well, the particles localize gradually, which means that the momentum distribution gradually becomes broader. The peaks flatten out, get bigger, and that's what we have. Or we could say, maybe it's like in the localization transition in equilibrium, where maybe just over time, the background gets bigger, and the sharp peaks just stay sharp, but they decay down. Or number C, something entirely different happens. So who thinks it's A, the peaks just get broader? One person. Who thinks it's B, the peaks just shrink and the background gets bigger?
I would think it's A, but since you created the suspense, I'll say something completely different.
So who thinks it's C? And who wants to finish with better coffee? So here's what happens after 5, 15, 25 microseconds. You just get more peaks. The peaks stay sharp, but you just get more and more of them. And in some sense, when you think about what I said about the structure momentum space, this kind of night moves on this fractal chessboard, that's exactly what you have. The system cannot just go from one momentum to the next momentum to the next momentum and broaden out. The only thing that it can do, if you neglect the trap, is this discrete jumps by 2h/k in 8 directions, which means it can only go from this momentum to any of the 8 momenta around it, and from this one to 8 of the momenta around it, and so on and so on and so on.
So it's one notable thing about the T equals 0, the starting point for there, is that it's way more regular looking than your diffraction. You know, just the initial diffraction. You know, it seems very clean. Whereas the stuff that happens later, where you're occupying a lot more winter groups, has this sort of chaotic aspect that the other thing has. So are those is that fact related really just exactly what you said?
So the fact that geometry that I get these distortions and they become more visible at higher orders, that's directly plays into it here, because here I have much higher order, so I see them more than I see them there.
Yeah, so here basically the atoms are localized is in the low order zone.
So here initially the atoms are not localized. Here the atoms are
They're not localized spatially, but I'm saying they're in the low momentum.
they are yes and no. So I think you have the right intuition. They are the thing is, if I want to talk about my momenta, say I have this momentum here, and then I have the 8 momenta around it. I hope it's 8, could also be 7 now. So let me call this the 0th order peaks. Let me call this the first order peaks. And then around each first order peak, I have 8 second order peaks and so on. From this one, I can go to the third order peaks and so on. So what you have in the BEC is initially true that this mostly occupies the low momentum orders. So first order, second order, and so on. While after the quench, I get to higher and higher orders, third order, fifth order, ninth order, and so on. So in some sense, this is very related to what we did earlier. And the thing is now funny, because when I just let this continue, I just get more and more of the sharp peaks. And in some sense, the system in the end looks localized to us because we can't resolve the sharp peaks anymore. So it's a little bit like if you have entanglement, it's good. If you have more entanglement, it's even better. If you have too much entanglement, it's just thermal entropy. It's a bit like this. You have this kind of plane wave that you start with your BEC with a small admixture of higher order plane waves. And you very controllably get more and more of those plane waves into it. But at some point, you have so many of these discrete plane waves that all you see is this localized blob coming out of this. So it's a very neat way of really thinking about how the localization happens in this case. It happens via proliferation of sharp peaks, which eventually you cannot resolve anymore. It's a bit like in a thermal state. You just call it a thermal state because you can't resolve all of the intricate entanglement patterns between all of the components. So ultimately, as I said, it's Q squared peaks, which lie dense in R squared. So it's still countable set only. So in that sense, it's still measure 0, but it's everywhere nonetheless. Okay. Another thing, just purely experimental for 1 minute, is to say, okay, we would love to, of course, see the lattice in real space and see the atoms in individual lattice sites. And you can't use a standard quantum gas microscope because you can't do the Raman sideband cooling. Every lattice site is different, so you would need a different Raman frequency for every lattice site, which of course you can't do. But what you can do is the quantum gas magnifier technique, where you have all of the particles, here's this array, periodic lattice now, in an harmonic trap, let them oscillate for a quarter period, that they're all here in the middle, then switch off the trap, and then they all fly off with this momentum and generate like a bigger version of your system. And we can do this, and these are the pictures we get. This is the superfluid, where it's maybe hard to resolve the individual peaks. And then here later on, this is in the Bose class phase, where you can really nicely see all of the individual peaks. You can see a lot of octagons in there. So we really see what's going on. And we're actually analyzing this at the moment. So many of the octagons that you, for instance, have here, like this one, you can see in here. And you have less peaks deep in the Bose class than you have in the superfluid, because the superfluid really occupies almost all sites, while the Bose class, where the tunneling is less important and the potential energy takes over, really kind of concentrates on the deep lying sites at low energies. And we can, like with using the tight binding model, really now look at this quantitatively, and in 2 months or so, there will be a paper in the archive about this. Okay. This was the light relief. Now let's get back to many-body physics for the last 5 minutes. Does many-body localization, can it exist in 2 dimensions? The story goes that in real random cases, you would expect it not to exist in 2 dimensions, because if you take this huge collection of random numbers, you will always have like small domains, small enclosures, where all of those random numbers are very similar to each other, just by chance. So you get this rare ergodic bubbles, and then Wojciech and others, Wojciech de Roek and others, they put out this kind of idea of the many-body delocalization via the quantum avalanche, where the idea is that once I have this kind of little ergodic domain, a small thermal system in here, that can destabilize and delocalize and thermalize more and more and more of its surrounding, and thereby it grows, gets more powerful, and that creates an avalanche that takes away the whole localized system. So that's why many people, when you now talk to them, say, well, you can't have MBL in 2D. We know that the quantum avalanche picture means it can't happen. And I'm not arguing with this. I'm just pointing out that if I don't take a random system, but if I take a quasicrystalline system, they are free of those conventional rare regions, because we know the distribution of on-site energies and how they change relative to each other. We know that we will never have such a domain in there to begin with. So we might never get this avalanche. So if you want to look at localization in 2 dimensions, quasicrystalline systems or quasi-periodic systems are the way to go. And in fact, there is just a few weeks ago a paper on the archive from Yijun Chon's group in South Korea, where they really look at, for various system sizes, the localization transition for real random cases and quasi-periodic cases experimentally. And they seem to see that for the real random case, the critical disorder strength flows, which means that for bigger and bigger systems, you need more and more disorder strengths, while they seem to not see that for the quasi-periodic case, which is, of course, very nice. And really gives us hope that there's a lot of stuff to be done here. What we can say from our experiments is not yet much about ergodicity, but we can say something about thermodynamic adiabaticity. What do I mean? Normally, if I go through a quantum phase transition, say from a superfluid to the Mott insulator, a typical test as an experimentalist is if I do it right, I have not heated the system, I can also go backwards, and I should end up and come back to my superfluid. And just to prove that we can also do this is if we start in a 3D cubic lattice in a Mott insulator, we get a big featureless blob. But if we ramp down over finite time back into the superfluid peaks come back. If we now, on the other hand, think about doing the same thing in the Bose class. So you think about your superfluid regime, you go into the Bose class, and then you go out of the Bose class another way. Then what I said earlier on about the Bose class not being ergodic, about the Bose class not being able to respond to changes because it has this non-local rearrangements that are needed, then I would expect that it should be impossible for the Bose class to do the same thing. I would expect that it would be impossible for the Bose class to be traversed adiabatically. What I kind of expect is that even if I do everything correct as an experimentalist, ramping into the Bose class is a one-way street, because that necessarily generates tons and tons of entropy, because it's a non-ergodic phase, which I claim, and therefore it cannot react adiabatically, and then I cannot come back out and get a superfluid. And we did the experiment. So what we did is we say start in the superfluid regime in our quasicrystal, and then transform the quasicrystal into a 3D lattice by just ramping down the diagonal beams. And if we do this, we get nice superfluid order back if we start in the superfluid, even after very, very short times. Which is maybe, okay, it's what you expect. Because if you have the superfluid, you have long-range order in your system. That you now locally have to rearrange your wave function from quasi-periodic to periodic doesn't mean anything that sites far away from each other are still correlated, and that correlation can stay the same way it is. So you would expect to be able to do this fast. If, on the other hand, you go into the Bose class and you try to come back, then it turns out whatever way you do it, you'll never get back to a nice superfluid. So going through the Bose class experimentally always generates a lot of entropy. What we got here is now a similar phase diagram to what we had before, where we're really asking, okay, this is a sign I should finish soon. We're really asking, okay, if I start in the superfluid, I ramp into the 3D superfluid, oh yeah, I get a nice superfluid back, I can be adiabatic there, even in very short times. But if I go to the Bose class up here, I cannot do that. So this is a very strong sign that I cannot traverse the Bose class adiabatically, which is totally consistent with the Bose class being non-ergodic, but it doesn't prove it yet. I would claim that if I am non-ergodic, I must be non-adiabatic, I can't be adiabatic, but the other way around, I can't prove right away. So that's something where like lots of discussions and lots of work is still needed. So if I just muse for the last 10 seconds a little bit about how localized phases can look in 2D as a function of the energy and of the interaction strength, well, I have the Anderson insulator at all energies in this case up here, in the non-interacting case. If I look for interacting cases, we do have the Bose class, which we traditionally say is just a ground state phase. We do have MBL, which we traditionally say covers the whole spectrum, must live very high up in energy. And they're like typically discussed by several different people in different communities using different language. And it sounds like they have nothing to do with each other. However, that's not very natural. What I'm saying is I think that if the Bose class turns out to be non-ergodic, then the more natural picture to think is that the Bose class really is a low energy limit of some kind of 2D MBL. Now, there's a lot of open questions up here. Will you really have MBL in the middle of the spectrum, or will you have a localization transition? Or is maybe the Bose class in the end also weakly ergodic and you just can't look for long enough and so on? I think there's an awful lot of things that we should look here, and it's a very exciting thing to look at. The hard point, of course, is that it's 2D, so you can't really do numerics. But we should really work together and try to really understand those things at a much, much better level. And that's basically the end of my talk. I have also some experiments in the group where we work on cardinal lattices and triangular lattices. So if you care about frustrated systems, happy to talk about that, but that wouldn't fit into this talk. Thank you very much.
Thank you very much. Questions? Yes. Mostly, it's a simple question. Like, is there a particular reason you use 4 lasers and not just 2 in 2D? Like, you can do 2 lasers. I mean, typically experimentalists try to minimize the amount of lasers they use, and you seem to double it.
If you just use 2 1D lattices.
2 incommensurate, yes, in some angle, which is also not.
If you take 2 lattices in any angle you want, you'll always end up with a periodic lattice.
No, but incommensurate lasers.
And okay, if you take 2 incommensurate
lasers, angle which is not 45 or 90.
Then the experimentalist will tell you that I have 4 beams, but they all come from the one same laser, so they all have the same wavelength. So in that sense, now it's easier for me. Plus, I wanted to have the 8-fold.
So more is easier. Okay.
Yeah. But it's only one laser, not 2 lasers.
And many optical links.
Yeah.
Okay,
Only one laser.
one reading of more euros.
Yeah.
Can you elaborate more a little bit on the Bose glass not being ergodic? We're talking about 0 temperature, right?
Okay, so yes, the Bose class originally was just really strictly about the ground state. But then if you look at it like in any thermodynamic phase, you can ask yourself, will it be stable to small temperatures? If I put like small energies, I should not talk about temperature. If I put small energies in there, will it stable or will it change? And there's a couple of works Laurent Sanchez-Palencia, for instance, and others have done quantum Monte Carlo simulation, which really tell us that the Bose class phase extends up to some finite energy. So therefore, it makes sense to talk about that phase not only strictly in the ground state, but really give it some space to live in. And that's also experimentally extremely important, because if what I'm saying about this non-adiabaticity is true, I have no chance of ever getting to the ground state of such a model. Right? Because if I go from superfluid into that phase, I'm already above the ground state and not in the ground state.
Maybe a naive geometrical question. So you mentioned this arrangement of C8 symmetry class, right? Like this 8 lasers.
With this full symmetry, yes. Yeah.
It full symmetry. So what was the reason to make it really this symmetric? Like, can I distort it? Like you mentioned that in the ninth order, if I have this one degree deviation, that it will be 9 degrees, whatever. But is it just because you would like to simply calculate where your bright peaks are, or it's just what will happen if I break this symmetry?
What will happen if I break this? At low orders, nothing. At low orders, nothing, because all points will just shift. Yeah. It's just the point what I have to make sure is that the angles still stay irrational, that I don't hit any accidental degeneracies, which then couple me in higher orders and make me periodic again.
Yeah, you turn around your 4-dimensional lattice and you project with different angle, right?
Yes, you either turn around or you say your 4-dimensional lattice is not simple cubic anymore, but your 4-dimensional lattice has like smaller angles. Yes, nothing topological happens.
Yeah. Okay.
Yeah.
Let's pretend to use them.
Yeah, so this question about the Bose class and adiabaticity. So, I mean, how can you be sure that the fact that you don't find that you can be adiabatic is not an experimental problem, so that you are just not waiting enough? So essentially that the time scale to be adiabatic in this case is way longer than anything that you can do. And
okay, 2 arguments. The first argument is that we know the characteristic time scale if we are at low entropy to generate coherence. This we know from if we start with mod insulator, where you really have particles localized to individual lattice sites. So we know the time scale over which coherence can emerge. This we know. And we look at the relaxation that we see in the Bose class. A little bit of relaxation is there. And now here we're waiting like whatever 4 times longer. So we would say this looks already pretty flat. Now, the second point is, of course, if I want to play devil's advocate, as long as this is a finite system, the Heisenberg time is finite, so I can always wait long enough and do things adiabatically. But that's just because of a finite size effect, right? My point is that in the thermodynamic limit, and this we can prove, in the thermodynamic limit, if I start with, for instance, this case here, yeah, this is the one. If I'm thinking about what happens if I go, I'm here, and I switch on epsilon interactions, and the particles will go into the second lowest side. I can calculate where the second lowest side is, and in the thermodynamic limit, it's infinitely far away, which means the time scale for the system to rearrange when I adiabatically try to switch on epsilon interaction must diverge, because particles must go from here to...
Yeah, but that's not the way you are doing it in the experiment. You are starting from the delocalized and then you are turning on the ramp. This is the opposite direction. Yeah, that's not the same.
That's not the same, true. But this is just a theoretical argument that at least in some parts of the Bose class, the timescale must diverge. Now, the question of, is the Bose class more structured internally and has regions where the timescale diverges and regions where the timescale does not diverge? So far, we've seen no indication that that should be the case.
More? Okay, if not, let's thank the speaker again. And if you are not already locked inside, see you tomorrow.